Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on strain gauges. We have looked at in the last class strain gauge as a system consisting of the metallic grid supported by a carrier and which is bonded to the specimen by a suitable adhesive. We have looked at quick setting adhesive like cyanoacrylate. Then we looked at epoxy, which is meant for sophisticated installations like in transducers, where you need to provide a very thin bond line, and also it should come for longer periods of operation. Then we looked at polyester adhesive. Now, let us look at the ceramic cements. And when you look at ceramic cements, they are useful for high temperature application or in radiation environments. See, now nuclear power is becoming very important. So, you need to live with radiation environments in such installations, and in such applications organic adhesives cannot be employed. So, you need to necessarily go for ceramic cements, and one of the popular ceramic cement is NIST X142, which exhibits high resistivity up to 980 degrees centigrade. We have earlier looked at some of these common alloys, Advance and Karma, they can go up to 260 degrees centigrade. That is only their metal foil, and the associated carrier we looked at was polyamide or epoxy or any such carrier. For any one of the high temperature application, you need to find a suitable metallic foil as well as an adhesive. Now, we are looking at the adhesive, we will also look at the special type of strain gauge and also the special process by which you could spray the ceramic cement. And what you have here is the constituents of NIST X142 is listed here. You have alumina, you have silica, you have chrome anhydride, and you have a colloidal silica solution, and you also have orthophosphoric acid. So, what you have here is you have the blend of ceramic powders such as alumina and silica combined with the phosphoric acid is mixed with a solvent such as isopropyl alcohol and an organic binder to form a liquid. So, essentially you have this ceramic available as a liquid, so that it is easy for you to apply it by a spraying process. And what you do is, on the specimen you provide a pre-coat of the ceramic cement. After application, it is fired to form a thin layer between the gauge grid and the component. So, it is a very elaborate process. You need to have proper training to handle this kind of special cements. So, once you form a thin ceramic cement layer on the specimen, you place the gauge, and the gauge is also very special. We will have a look at it little while later. And what you have is, you have to remove the carrier of the gauge and place it on the thin layer of ceramic, and a second layer of ceramic cement is then applied. So, you have an initial layer of ceramic on the specimen. Your normal carrier of the gauge will not withstand such high temperature. So, the carrier of the gauge needs to be removed, and you put a second layer of ceramic cement to bond the gauge. And when you do something like this, gauge resistance to ground will be only about 6 megohms. It is much smaller, but that is the best that you could get when you use these kind of ceramic cements. So, what you see here is you need to have a strain gauge such that its carrier can be removed. And you have an example of how such a gauge can be constructed. I have a sketch here. I essentially have a wire type strain gauge, and you have a Teflon tape carrier which could be peeled off, and you make a decent sketch of this. So, what you have here is gauges are constructed with a grid fabricated from wire, which is mounted on slotted carriers made of glass reinforced Teflon tape. So, why you have slotted type is you put a layer of ceramic, then the strain gauge would be bonded. At that time you can remove this Teflon tape, then again do a coat and complete your installation. And in order to apply the ceramic, you need to have a special gun, and as I mentioned earlier, the tape is removed after the grid is secured to the component. So, it is a very involved process, it is not like simple strain gauge bonding. Since you have to work at very high temperatures, you need to have a systematic procedure. Here we look at one family of strain gauges which could be used for high temperature. There are also weldable strain gauges which we are not paying attention now, but you should know that for high temperature application you also have another form of strain gauge which could be welded to the base material. Here we only look at forming a layer of ceramic and remove the carrier and again put another layer of ceramic, so that the gauge is properly bonded, and you have such gauges available commercially. And this is given by Vishay Micro Measurements, and they have what is known as Kanthal, which is meant for high temperature strain gauge, and you could see the slotted Teflon tape carrier, and you have the strain gauge available like this. So, this can be used to put the ceramic cement and remove the carrier and put another layer. So, essentially you will have only a ceramic base and you will have a metallic foil. There is nothing like a polymer that comes in between. So, at such high temperatures they will not withstand that, they will disintegrate. So, in order to make sure that your instrumentation is good at that high temperature, you form a ceramic layer. And how do you do this application of ceramics? So, you have a special gun which is a modification of your gas gun and you feed the alumina as a rod. So, you have a ceramic material in rod form is fed into the combustion chamber, and because of the high temperature the rod decomposes into softened semi melted particles, and you can actually have a closer look of this. So, you have the ceramic rod, you have oxygen and acetylene, and at the outlet of the gun you have a atomized spray of ceramic particle. That is what you get. The idea is to get a fine spray and spray it on the specimen, and by changing the rod you could apply it for different temperature ranges, that also we will see. The material that you use for the rod, if you change it, you can work for different temperature regions. And what you find here is you use a pure alumina rod for high temperature applications. On the other hand, if you use a rod which has 98% alumina with 2% silica, you could use it for applications below 425 degrees centigrade. So, what you have in this process is the ceramic material in rod form is fed and you have an atomized spray of these particles, and the particles impinge on the surface of the component and forms a continuous coating. It is again a very special process, it is not like a simple spray gun, you have to handle it carefully for you to form a thin layer of ceramic. Now, what we have looked at is we have looked at the strain gauge system, the system consisting of the metal foil, carrier and the adhesive. Now, we will have to look at how this system functions in actual practice, what considerations that we need to look at while selecting the constituents of the system. Depending on the application, I must select a suitable alloy, suitable carrier and also a suitable adhesive. For high temperature, the selection is very simple. You know that you can't use epoxy or polyester as adhesive, you need to go for ceramic cement. But even from stability or hysteresis or linearity point of view, the constituents play a role. That is what you have to look at. And I said strain gauge selection is a very important aspect that you need to learn. And for strain gauge selection, you need to have a background, what is the role of each of the constituent. Though this information is descriptive, that information is also needed from the point of view of selecting the appropriate system for your measurement. And we have already looked at you need to worry about strain gauge linearity, hysteresis and zero shift in any strain measurement application. And what happens to the magnitudes of these, like deviation from linearity, hysteresis and zero shift? They all depend on various factors. What is the strain level at which I operate, whether the bond is adequate, so that strain transfer from the specimen to the strain gauge is effectively carried out. And if you look at the property of the alloy, what is the degree of cold work of the foil material, and naturally the viscoelastic characteristics of the carrier material, because we say that deviation from linearity, hysteresis, they all become very important in transducer applications. and you will find by changing the suitable carrier, it is possible for you to improve some of these aspects. That is why I said you should view strain gauge as a system consisting of the alloy for the strain gauge metal foil, then you have the carrier, then you have the adhesive. Selection of all these three are interrelated. Depending on the application, you should select it appropriately. And what I have here, suppose I want to minimize deviation from linearity, then choose an appropriate carrier. What you find is polyamide carriers, the deviation is about 0.1%. On the other hand, if I go for epoxy carriers, it is just half of it, it is about 0.05%. But you know very well polyamide is easy to handle, it is a plastic, even a beginner can handle this polyamide carrier. We have already looked at epoxy is brittle, that is recommended for transducer applications. So, what you find is when I want to improve linearity, hysteresis, zero shift, I need to go for sophistication. It comes with a price, it does not come freely. And we have also looked at strain level plays a role, and what is observed is hysteresis and zero shift strongly depend on the strain range, and that is what is illustrated in this graph. You can have a look at it. So, what I have here is on the x axis I have number of cycles, and the y axis you have cumulative zero shift, and the graph is plotted for a strain range of plus or minus 1000 microstrain, then another graph for 1500 microstrain, and the third graph for plus or minus 2500 microstrain. It is very high, it is going beyond elastic region, because 2000 microstrain is the strain range at which you have plastic deformation takes place. So, what you find if you closely look at, there is an initial slope, as the number of cycles increased you have a gradient and then it becomes horizontal, make a note of it. How do you use this information for strain gauge instrumentation? What is the recommendation? That we will see now. The recommendation is, we find that the zero shift changes in the initial few cycles. So, you have zero shift per cycle is much larger during the first 5 to 10 cycles, that is what the graph shows. So, what you do is, it is recommended that a strain gauge installation be cycled to 125% of the maximum test strain for at least 5 cycles. So, you do not go and make the measurement as soon as you paste it and the strain gauge is ready for measurement. You find that adhesive is completely cured, you do not go and do the make and the measurements. The advice is you do a strain cycling, particularly when I am making a transducer, I will do the calibration at the factory itself, wherein you load it beyond 125%, do a few cycles and then ensure that the system as a whole is stabilized, then release it for actual measurement. Even in your regular test conditions, it is recommended that you do a strain cycling before you make final measurement. From where this knowledge comes? You find the zero shift is a function of the cycle. Initially the zero shift is more, after about 10 or 15 cycles, it stabilizes. So, the recommendation is at least do 5 to 10 cycles. If you can do more, that is well and good enough. So, that is what you get from looking at your observation on zero shift as a function of the strain range. Now, we get on to another important issue in all strain gauge installation, that is stability. This becomes very important in applications when you have to record strains over a period of months or years. It is not just that you do the strain measurement for immediate requirement and forget about it. Suppose I want to monitor structures like dams and bridges, we may have to do it for long periods of time. And in such applications, there may not be an opportunity to unload the specimen and recheck the zero drift. So, in such applications, it is better that you select a system that is stable for such applications. And when I say the strain gauge system, I have already said you have to choose the proper alloying material of the strain gauge, the type of carrier as well as the adhesive. All three go together. We will see a nice example where people have conducted experimentally for a long period of time different alloy as well as the backing and the adhesive. When I change one after another, you find there is significant improvement. So, in applications where you have to record strains over a period of months or years, the stability of the strain gauge system as a whole has to be looked into. So, when I say system as a whole, you should pay attention on the selection of proper alloying material, the type of carrier as well as the adhesive. And you have a nice example. I have a graph which shows time versus zero shift. Time is plotted in a log scale. I have 10 days, 100 days and 1000 days. And I have 3 graphs. I have one graph for strain gauge alloy is advanced grid and polyamide carrier, and the second graph is the grid material is same, it is again advanced grid encapsulated phenolic glass carrier. The carrier is made different. You have the encapsulation and you have the phenolic glass carrier. It is much better than the polyamide carrier. So, what you find? You see a very significant zero shift in a simple advanced grid with polyamide carrier, which is substantially reduced when I just change the carrier material. And the third graph, which is almost close to 0, that you get from Karma grid encapsulated with glass fiber epoxy phenolic carrier. So, what you find here is by changing the strain gauge alloy, what you find finally the system as a whole has improved. From the first graph to second graph, you found that the carrier has indeed improved. A further improvement is possible by changing the alloy itself. So, that is where I said you need to look at strain gauge as a system, and you have a summary of the observation of the graph, which is available in the next slide. And what you find here is a zero shift of the order of 270 micro strain. is observed after 30 days for advanced alloy with polyamide carrier. And if you look at the installation was waterproofed well. There was no difficulty of moisture entering into it and deteriorating the strain gauge bonding. And what people found was the carrier is not taking the load properly. So, there was stress relaxation which has caused the drift. And when you are making a measurement, 270 microstrain is very high. If the zero shift itself is 270 microstrain, then what level of confidence you will have in the final measurement. So, for a given application, you need to find out, have you selected the right combination of strain gauge alloy, carrier as well as the adhesive. And you see in stages, initially we saw 270 microstrain, which is very bad. Now, I go and improve the carrier. Instead of polyamide, if I use a glass fiber reinforced phenolic carrier, the drift has reduced from 270 microstrain to 100 microstrain even after 50 days. In fact, that is what is listed in this graph. This is about 270 microstrain, this you see at the end of 30 days, and at the end of 50 days you find only 100 microstrain by just changing the carrier for the strain gauge. So, whatever the stress relaxation, the glass fibers eliminated that effect. And also the whole test was done at 75 degrees centigrade. See, we have already noted that advanced alloy is a good strain gauge alloy for room temperature applications. And they also noticed that drift was due to instabilities in advanced alloy at the test temperature of 75 degrees centigrade. So, once you notice this, change the strain gauge alloy to Karma grid, but retain the same carrier with encapsulating glass reinforced epoxy phenol carrier. Zero shift was only 30 microstrain after 900 days. So, that means it is almost like 3 years, 2.5 years. For 2.5 years, absolutely no problem in your strain measurement. But when I take Karma grid, what happens? It is difficult to solder the tabs. So, you need to go for the factory supplied lead wires. Strain gauge also comes with pre attached lead wire systems. So, you need to go for that kind of a strain gauge for you to use in such applications. So, all that is expensive. See, if you go and solder your own lead wire, the costs are less, but if you have to get the pre attached lead wire, cost is high, and glass reinforced epoxy phenolic carrier is again expensive. So, when you find your application demands high stability, then it is worth spending money for such applications. So, you need to select. You cannot take things for granted, stability is an issue. So, you need to worry about what temperature that you are working at and what backing that you are using and what adhesive. Here the adhesive role is not emphasized that much, and what you find is Karma grid has worked at 75 degrees centigrade quite well. Even at room temperature, instead of positive drift, it has a negative drift of minus 25 microstrain. See, what you have here is for long term measurements, Karma grids with glass fiber reinforced epoxy phenolic carriers with a well cued epoxy adhesive system is recommended. So, I said that adhesive has not been mentioned, but what you find here is for any sophisticated applications, people go for epoxy adhesive, and you should also ensure that the gauge installation is waterproof well. You do this to minimize moisture penetration. Not only this, see, we have already seen in a strain measuring instrument, I need to have completion resistors. The bridge completion resistors should be hermetically sealed to ensure stability of the bridge. See, the idea is you have taken care of the strain gauge installation, you have selected the right type of alloy, carrier as well as the adhesive. But now you have to make the measurement using a Wheatstone bridge, and Wheatstone bridge has completion resistors, because in many applications we may do only a quarter bridge. The other 3 resistors are there in the Wheatstone bridge, and these have also to be waterproofed well, because you are trying to make the measurement for long durations. Sometimes you may ignore this, you may take it for granted that my instrumentation will automatically take care. So, you need to go for properly sealed completion resistors for such long term applications, it is very important, and this completes. So, what you find is, for stability go for Karma grids with glass fiber reinforced epoxy phenolic carriers with well cued epoxy adhesive, and also ensure in your bridge completion resistors to be hermetically sealed. Now, we move on to one of the other important aspect in strain gauge instrumentation, namely heat dissipation. See, when you come to thermal effects, you need to deal in 2 effects. One is I work at moderately high temperature than the room temperature. Suppose I want to measure strains on IC engines, then I may have to put it at the IC engine block and find out that temperature will be higher than the room temperature. So, in such applications I should measure the temperature by a thermocouple, and then either look at thermally induced apparent strain and subtract it, or put another strain gauge which is at the similar temperature and make it as a half bridge and handle the thermal effect. This is one type of thermal influence. The other type of thermal influence, what you need to worry about is heat generation due to I squared R loss. This is very subtle. See, in many applications, if you are working at high temperature, compensating for that you may do it more by a routine, because that is very obvious. What is subtle is, because current flows through the conductor, the strain gauge itself get heated. This is a very subtle issue, and you need to find out what parameters that influence. Even the selection of the grid size can matter, and what is the voltage that I apply to Wheatstone bridge for making my measurements, that also can influence. So, here again you have to look at system as a whole and find out a remedy. And why we need to worry about this? Whatever is the I squared R loss, this causes a change in temperature, which in turn causes a change in the resistance of the strain gauge, thereby spurious strain signals would be produced. So, I need to eliminate these spurious signals, and this is the most challenging aspect of strain gauge instrumentation. And from this point of view, heat dissipation assumes importance. Whether you like it or not, strain gauge get heated, and you need to look for how to dissipate this heat generated. What are all the parameters that I have to look at, so that I minimize any temperature rise because of buildup of heat due to I squared R loss. That is the focus. and it depends on various factors. The first factor is what is the gauge size. If you look at the catalog of strain gauge by the manufacturers, you will find gauges of various width and length to suit different applications. The second aspect is what is the configuration of the grid and what is the spacing and size of the conducting elements. See, when you say the configuration, I had already mentioned I can have a rosette with strain gauges separately aligned, and I can also have them as stacked. And from measurement point of view, the approximations involved in idealizing the point on which you make the measurement, stacked rosettes are better. But stacked rosettes bring in another problem. The heat generation will be much more in a stacked rosette than the normal rectangular rosette, where they are kept slightly away from the point of interest. They meet at a point of interest, they are not exactly on the point of interest for which you want to make the strain measurement. So, grid configuration matters, and what is the type of carrier, and what is the type of polymer, and what is its thickness. You can also say the similar thing for the adhesive, and if you look at the specimen material, that also plays a role. Am I working on copper, or am I working on steel, or am I working on plastics? The specimen material matters. Not only this, I may work on copper or I may work on steel, but even the specimen volume at the point of interest matters. If you have a very thick block of copper, then heat dissipation is not at all a problem. So, apart from specimen material, specimen volume also plays a role, and we have always been saying whenever you do a strain gauge installation, we must provide a proper coating so that changes in weather does not affect your installation. That is good from one point of view, it prevents moisture absorption. From heat dissipation point of view, what is the type of weathering you use and what is its thickness also plays a role, because if I put a very thick weathering coat, you are not allowing heat to dissipate. On the other hand, if I have a high velocity of the air flowing over the installation, it is well and good. So, the manufacturer also looks at it differently. They recommend what is the allowable power density, that is the way they look at it. So, you have a power density defined as P by A. P is the power to be dissipated, that you can calculate from I squared R loss, and A is the grid area. See, later we will also go and see selection of strain gauge, where we will see a variety of patterns, and you will find you get gauges of different grid area. Why such grids are available, you will know from charts that say for a given application and a given power density, what kind of grid patterns I can select. So, I need to look at and approach the problem scientifically. So, I have a parameter for a given type of specimen material and for the thickness what is mentioned, this is the power density that it can safely operate. And what you find here is, if I have a heavy aluminum or copper section, the power density permissible in watts per millimeter squared ranges from 0.008 to 0.016. And when I go for heavy steel sections, the power density value reduces, and when I go for thin steel sections, it reduces further, and when I go for poor conductors like fiberglass, glass, ceramics or unfilled plastics, the power density permissible is almost close to 0, it is very small. So, you need to have very efficient heat dissipation, and that is the reason I said if we have to work on composites which are becoming very important structural members, you need to go for higher strain gauge resistances. And mind you, when you go for higher strain gauge resistances, they are also very expensive. It is not cheap, because we have already looked at making a small strain gauge with even 100 ohms, you needed a longer wire. So, if I want to have 1000 ohms at the same place, unless I improve my technology, it is not possible, and when improvement technology also demands high cost. So, if you want to go for the sophisticated applications, you need to go in for higher cost. There is no other way that is available for you. So, this is what you have to look at. Allowable power densities are strongly related to the specimen. That is what this table essentially brings out. So, in a strain gauge installation, I said strain gauge as a system consisting of grid alloy, carrier and adhesive. Now, you find from heat dissipation point of view, even the specimen material dictates, and the manufacturer supplies you with such complicated graphs. I will try to explain it in a very simple fashion. So, on the x axis you have a grid area. I will also enlarge it a little while later. First, on the x axis note that you have a grid area, on the y axis you have the bridge excitation voltage. So, my idea is to find out the excitation voltage, so that I satisfy the power density requirement. And what you have here is, on the graph you find slanted lines. These lines indicate different values of power density. So, if you look at it zoomed, so what I find here is, I have a line for 0.01 watts per inch square, or it is 0.016 kilowatt per meter square, and the power density increases in this fashion. So, if I know for a particular specimen material only a particular power density is permitted, then this tells me what kind of gauge patterns which I can choose. I suppose you are able to see these letters, if I are not, I will be able to enlarge it, and what you find here as 250 AE, 250 AF, they indicate first is the length of the gauge length expressed in mils, and AE, AF, DA, EA, all this pertain to particular strain gauge manufacturers classification of the grid pattern. You have so many grid patterns, they churn out many different grid patterns, and for each one of the manufacturer will provide you a graph like this for you to select the suitable grid pattern and also decide on the selection of bridge excitation voltage. And if you look at the graph, you have a cluster of gauge grid identification here, you have another cluster of gauge grid identification here. This is essentially grid area. You could have a wider grid, you can have a narrow grid, you have different type of patterns. Your measurement application will decide whether you need a wide grid or narrow grid, all that decisions you will have to take. And if you also look at this graph is available for 120 ohms, and this is a particular graph for 120 ohm strain gauges. Suppose I go for 350 ohms strain gauges, these power density graphs get shifted. So, that means I can afford to apply a higher voltage for the same power density if I use a higher resistance of the strain gauge. And you also have another graph for 1000 ohms. This is just to give you an idea, such selection graphs are available from the manufacturer. So, how I go about and select the bridge voltage? If you look at most common strain indicators, use bridge voltage between 3 to 5 volts. Small gauges mounted on a power heat sink result in lower allowable bridge voltage. So, that is the reason when we had a discussion on selection of gauge length, we saw if the strain is varying linearly, length of the gauge length do not matter in interpreting the strain at the center of the strain gauge. Only when there is a nonlinear variation, then I need to worry about selecting a suitable gauge length. And I also caution, when you select a smaller gauge length, it is expensive, difficult to make, and in addition you need to worry about what is the bridge excitation voltage that you can select, and also make special provisions for heat dissipation. You must allow a stream of air for you to cool the strain gauge installation, or some such special attention you need to pay. And suppose you are unable to improve your heat dissipation from external means, you can at least think of using a higher resistance gauge or a gauge with a larger grid area. This is the kind of selection compromise. See, if I have a larger grid area, then I am deviating from idealizing measurement of strain at a point. I am measuring it only through a area. This is possible only when the strain variations are small as a function of distances. So, selection compromises always exist. Without compromises, you will not be able to handle a problem. Now, we have talked about influence of temperature in some form. We should also look at what is the sensitivity of the gauge to temperature. What happens when the temperature changes? The strain sensitivity SA of the metal alloy used for the grid changes. We will have to see how does it change, that is the question. And for simplification, for a change of plus or minus 10 degree centigrade, the variation of SA is usually neglected. And it is obvious, depending on the coefficient of expansion, when the temperature changes, the gauge grid either elongates or contracts, specimen either elongates or contracts depending on the delta T. And you also find the resistance of the gauge changes, because we have earlier written the change of resistance to original resistance as Sg into epsilon. On similar lines, you write the expression St into delta T, and you label St as sensitivity of gauge to temperature. Sg is the gauge factor which is used in interpretation of change in resistance to axial strain. When I bring in effect of temperature, I bring in another parameter called St, which has to be evaluated again experimentally. How does this SA changes as a function of temperature? And what you find is, fortunately it is a linear graph. for the popular strain gauge material like Advance, Karma, as well as high temperature applications like nichrome, Armor D, as well as the platinum tungsten type of strain gauge alloy. Only for isoelastic it is non-linear. So, if it is linear it is good enough. So, you just make a note that Advance and Karma it is varying linearly, that is what you need to worry about. It is a variation is linear, fortunately it is linear. So, we can do some kind of correction in that. So, what you find in quantitative terms is change in the strain sensitivity of the conductor as a function of change in temperature is 0.735% per 100 degree Fahrenheit for Advance, it is minus 0.975% per 100 degree Fahrenheit for Karma. So, you have this data, it is possible because strain gauge is constructed based on a conductor. So, I need to know the conductor property, then I need to look at when I make it as a loop how does this changes. So, what we will look at is handling temperature information and segregating the change in resistance due to stress applied and temperature change is the most challenging aspect in strain gauge instrumentation. So, in today's class what we saw was we looked at how to use ceramic cements and what is the kind of strain gauge that you need to use for high temperature application. Then we moved on to performance analysis of the strain gauge system. I said you need to worry about deviation from linearity, hysteresis as well as zero shift, and we found the constituents forming a strain gauge influence these aspects. We saw selection of the carrier influences the linearity, selection of the alloy as well as the carrier and an appropriate adhesive can improve stability for a very long duration. So, selection is very important. Then we moved on to another subtle issue, how does temperature changes occur. One of the subtle changes is current flowing through the strain gauge itself can heat it up, and you find the heat dissipation is a function of the specimen material. Not only the strain gauge system, you should also consider on which material we want to operate, which decides selection of the bridge voltage, also indirectly decides the selection of the resistance of the strain gauge alloy, and also the type of grid, whether you want to go for a wider grid or smaller grid, or whether you want to go for stacked rosettes possible, or whether you need to go for unstacked rosettes only possible for this kind of heat dissipation. All those decisions are dictated by the heat dissipation capacity of the specimen material. So, this takes you a step ahead on how to do effective strain gauge instrumentation.